Okay, we're here with our student Rita, and how to write them as functions. Okay, ready to go, Rita?
Yes.
Okay, so first let's do a quick review of what sequences are. There's really two types that we're going to be talking about here. There's arithmetic and geometric. You might remember what those are, but let's review them really quick. First, before we even get to those two types, what's a sequence? Okay, a sequence is a list of numbers that are in an order and with a pattern, and you want to find that pattern. Okay, it's kind of like a puzzle for you. So let's first look at an arithmetic sequence. And an arithmetic sequence just means that it's going to be using addition and subtraction, not multiplication or division. Okay. And so here we have a list of numbers. And the thing you should know about a sequence, it has the first, second, third, fourth term just listed. And that's what that n means. So if n is 3, that means it's the third term in the sequence. And then the actual value of the sequence is written over here. Okay, and the cool thing is that what you really want to focus on with arithmetic sequences and geometric sequences both is the first term and then where you go from that first term, okay? So let's first write, for this arithmetic sequence here, what's our first term? Can you read that from the table?
Yeah, it's 3.
Good. Okay. Now, the thing about arithmetic sequences is then you're either going to be adding or subtracting the same amount to get to the next term, and then that same amount to the next term, the same amount to the next term. That is called the common difference, because it's the difference between any two values in the sequence, any two terms in the sequence, okay? So how much do we move to get from 3 to 7?
4.
4, and it's positive 4, right?
Right.
So that's probably the common difference. We'll write that there, but let's just make sure. Is that the same as 7 to 11?
Yes.
And 11 to 15?
Yep.
Okay, good. So we've kind of figured out the puzzle of this arithmetic sequence. Okay. Now a geometric sequence is a little bit different in figuring out the puzzle. It's going to have to do with multiplication and division. So here again we have the term and then the value. And we want to first find the first term. So what's that? Pretty easy now.
1.
1. Okay, yeah. And when we say that first one, remember we're talking about here, not this one over here. Okay. All right. Now with a geometric sequence, you're actually going to be multiplying or dividing to get the next number. So here 1 goes to 2. What are we multiplying 1 by to get 2?
2.
2. And then 2 goes to 4. What do we multiply 2 by to get 4?
2.
2. And then 4 goes to 8. What do we multiply 4 by to get to 8?
2.
2. So there's something called a common factor. It's the same one. It's common to every single step in the sequence. And that common factor is 2. It's what we're multiplying by. Okay? So those are your two kinds of sequence. And with each one, you want to pay attention to the first term. And then with arithmetic, it's the common difference. And with geometric, it's the common factor. Okay? Okay, good. Now, let's talk about using function notation and what that is. At first, it seems really intimidating, but it's actually a way to save you time. So it's a way of writing math statements that will save you time. Okay? Now, we won't go over all of how it saves you time here, but just remember that that's what it's for. So when you start getting intimidated by looking at this weird way of writing stuff, just get used to it, and eventually you'll be like, oh, thank goodness I have function notation rather than having to write this some other way. Okay? All right, so with an arithmetic sequence, we're going to write this in a particular way. We're going to say the function of the first term, the function of the sequence when you're talking about the first term, the value is 3. So we say f of 1 is 3. Okay? What would f of 2 be for this arithmetic sequence over here?
7.
Good. What would f of 3 be?
11.
11. Okay, that would be how we would write it here. And it would become a really easy way. Rather than saying, writing out the first term of the sequence is 3. The second term of the sequence, it's much easier to say f of 4 equals 15. Okay, so this is how it's saving you time. Now this next part is going to look a little intimidating, but just bear with me and I think you'll get it. Okay, I'm going to write out this statement here. I'm going to say that f of any term plus 1 is equal to f of that term plus 4. Okay, so we're going to use this variable n to refer to a term here. Now this might not make sense quite yet, but let's just think about this statement here. We're going to take any term, like let's say 7. We're going to add 4 to it, to get the next term. Okay, does that make sense?
Yeah.
So f of 2 would be 7 plus 4 would equal 11, which would be f of 2 plus 1, f of 3 equals 11. Okay? So this is kind of what might seem kind of like a fancy, confusing way to just say, to get the next term, add 4. That's all it's saying right here. And here it might seem like, that's not saving me any time. And it might not be yet, but eventually it will. Okay? Okay, so that's how you use function notation with an arithmetic sequence. Now let's talk about a geometric sequence. It's a little bit different. Do you think we'll be adding here, or what do you think we'll be doing? Multiplying or dividing, but with this particular sequence it'll be multiplying because we already figured out we're multiplying by a common factor of 2. So here our first term, f of 1, is 1. Does that make sense?
Yes.
Okay, and now we're going to do a very similar thing. We're going to say to get the next term, you're going to take the previous term and multiply it by what?
2.
Okay, so let's see if this makes sense. To get the next term, take your current term and multiply it by 2. Make sense?
Yes.
Okay, good. So now you're kind of used to function notation for sequences. Just practice will get you a lot more used to it. Now remember, with sequence, one of the coolest things we can do is predict values. So let's go over here. And remember that if you're going to predict values, you need to know that it's an infinite sequence, one that goes on forever with the exact same pattern. So we didn't say that over here, but if we had said this was an infinite sequence, you could say, okay, the 5th term will equal 19, the 6th term will equal 23, and you could go on forever and find the 5 millionth term even, okay? And same thing with this down here. So now let's talk about infinite sequences, and let's assume that these are infinite sequences over here, and let's try to predict values. What would the 6th value of this infinite sequence over here be?
It would be, let's see, 15 plus 4 plus 4, 23.
Yep, so we could do 15 plus 4 plus 4, because we are on the 4th. We have to go 2 steps down, so we have to add 4 twice, and 15 plus 4 plus 4, or 15 plus 8, is 23. Okay? Now, how about for the geometric sequence? What would the 6th value there be?
Let's see, 8 times 2 times 2 be 32.
Yep, so that's exactly what we have here. So 8 times 2 times 2, because remember we have to go 2 steps down, and with each step you're multiplying by 2, and that's 8 times 4, which is 32. Now, if I had said to you what was the millionth term, you would be here all day adding 4 one at a time, right? Or multiplying by 2 one at a time. There's an easier way that you'll learn later about how to convert this kind of confusing way of writing a function. This is called a recursive definition here. You can write what's called an explicit definition that makes it a lot easier to predict those terms that are weighed out in the future, okay? And the function notation for those ones is a little bit easier to get your mind around. You just have to start here first so that you understand it. Okay? So we'll look forward to that. Good job.